first topic is balancing of the redox reaction. First, if we balance the redox reaction through the procedure what we have discussed earlier, we can solve the problem very easily. But the drawback of that procedure is, if you just know the total reactants and products, we can balance the reaction, then we can proceed for numerical calculations. But sometimes if we do not know the actual nature of the products that are being formed, we can't balance the reaction. Therefore, even without the knowing the actual products that are being formed, we can solve the numerical problems related to redox reactions. How to solve the numerical problems related to redox reactions? So, in all the redox reactions, first you identify the what is called valence factor or N factor or change in the oxidation state of every reactant species. For example, let us take the KMnO4. When KMnO4 participates in the reactions, so KMnO4 will always gain the electrons. The actual number of electrons gained by the KMnO4 depends on the medium in which reaction takes place. In acidic medium, it will gain certain number of electrons. In alkaline medium, different number. In the neutral medium, totally different number. Therefore, if we just know the medium in which reaction is taking place, we can identify the number of electrons gained by the one molecule of KMnO4. So, for example, if the reaction takes place in acidic medium, one molecule will always gain 5 electrons, hence it converts into Mn2+. Since one molecule is gaining 5 electrons, hence we can call N factor or valence factor of the KMnO4 in acidic medium is 5. By using this valence factor, we can solve the numerical problems very easily. Similarly, KMnO4. When KMnO4 participates in the reactions in alkaline medium, one molecule will always gain 1 electron. Therefore, this KMnO4, it will be converted into K2MnO4 minus. One molecule will gain 1 electron. Next, KMnO4. When it participates in the reactions in the neutral medium, one molecule will always gain 3 electrons. Therefore, it will be converted into MnO2. So therefore, just if you know the medium in which reaction is taking place, we can easily identify the number of electrons participating per one molecule. That number of electrons participating per one molecule itself is called valency factor or N factor. By using this N factor, we can calculate the equivalence of the KMnO4 participating. Therefore, valence factor of KMnO4 is equal to number of electrons exchanged by number of molecules participated. Similarly, for K2Cr2O7 also always act as the oxidizing agent. But here, the number of electrons gained by the K2Cr2O7 is always fixed. Whether the reaction takes place in acidic medium or alkaline medium or neutral medium, one molecule will always gain the fixed number of 6 electrons. Therefore, here each chromium will become +3. Hence, valency factor of the potassium dichromate is 6. Valency factor. Similarly, oxalate or oxalic acid. When oxalic acid or oxalate participates in any reaction, one molecule will always supply 2 electrons. So this carbon and this carbon both will be converted into 2 CO2, here 2 electrons. Therefore, since one molecule is supplying 2 electrons, the valency factor of the oxalic acid is 2. Oxalic acid. Similarly, hydrogen peroxide. One molecule, hydrogen peroxide, it can act as the oxidizing agent as well as reducing agent. If it acts as the oxidizing agent and if it acts as the reducing agent, whether it acts as oxidizing agent or reducing agent. Oxidizing agent means electron gainer. So one molecule will gain 2 electrons. Here if it acts as reducing agent, one molecule will supply 2 electrons. Therefore, number of electrons participating per one molecule is fixed, whether it is oxidation or reduction. Now let us take one example to identify the valency factor and how to proceed for the calculations of numericals involved in these redox reactions. Let us say MnO4 minus permanganate is reacting with the oxalate C2O4 2 minus. Now the reaction is taking place in acidic medium. MnO4 2 minus, it will be reduced to Mn2 plus. Next, oxalate will be oxidized to CO2. Next, without the need of balancing the reaction, how to proceed to simplify the numericals? So, since the reaction is taking place in acidic medium, we know the valency factor of the MnO4 is 5. So, valence factor of MnO4 is 5. Next, the oxalate, valence factor of oxalate is always 2. Valence factor of C2O4 2 minus is always 2. So, if you remember the valence factor of a certain well-known species, we can easily proceed to simplify the numericals. Next, in every redox reaction, the equivalence of first reactant is always equal to equivalence of second reactant. Therefore, equivalence of MnO4 minus is equal to equivalence of oxalate. Equivalence, for equivalence we can use any suitable formula. For example, equivalence means weight by gram equivalent weight, or normality into volume, or moles into valency factor. Any one of these suitable formulas can be used to calculate the equivalence. For example, if the reaction takes place in the solution medium, equivalence of the KMnO4 is equal to equivalence of the oxalate. Here this is normality, this is volume. This normality and volume. So in the numericals, if they give the molarity, you try to convert that molarity into normality by using this relation. Normality is equal to molarity into valency factor. See, if you remember the valency factor, and if molarity of the reacting species are given, by using valency factor and molarity, we can easily convert into normality. Then from normality, we can use this relation. Equivalence of the first reactant is equal to equivalence of second reactant. So by using this formula, if they give the normality and volume of first reactant, if they give the normality, we can calculate the volume like that. So based on the equivalence principle, all redox reactions can be easily simplified. Similarly, let us discuss another example. Here ferrous is reacting with the dichromate. Now reaction is taking place in acidic medium. Here ferrous has been oxidized to ferric. This dichromate is gaining electrons. It has been reduced to Cr3+. This is the reaction. Here the valence factor of dichromate is 6. Valence factor of Fe2+. You see, one ion is supplying 1 electron. One ion has lost 1 electron, hence ferrous has been converted to ferric. Therefore, valence factor of the ferrous is 1. Therefore, while doing the numericals, by using this valency factor, we can equate the equivalence of the ferrous with the equivalence of the dichromate. Equivalence of Fe2+ is equal to equivalence of Cr2O7 2 minus. This in place of this equivalence, any suitable formula can be used. Suitable formula like weight by gram equivalent weight. This side, if you know the dichromate is in solution state, we can use this formula like that. Next, let us discuss another example. Iodine, it is reacting with the Na2S2O3. This is hypo. Here, the product is Na2S4O6. This is sodium iodide. Therefore, here iodine is upon reaction with the hypo, here the sodium tetrathionate and sodium iodide are being formed. Now, what is the valence factor of the iodine? Here in this reaction, one molecule of iodine is participating. The oxidation state of each iodine atom in the reaction is 0. Therefore, total oxidation state is 0. This side, each iodine atom is exhibiting the -1 oxidation state. Therefore, total oxidation state here is -2. Therefore, one molecule is gaining 2 electrons. Therefore, valency factor of the iodine. Valence factor of iodine is number of electrons gained. Number of electrons gained by number of molecules participated. Number of molecules participated. Number of electrons gained, 2 electrons, molecule 1. So therefore, valency factor of iodine is 2. Similarly, hypo. For hypo, see what is the change in the oxidation state of the hypo, reactant side to product side. For that purpose, we should have idea about the structure of this Na2S2O3. Based on the structure only, we can find out the change in oxidation state. I will show the structure first. This is sodium thiosulfate. This is sodium tetrathionate. Here the oxidation state of the sulfur is 0. Here oxidation state of the sulfur is +4. Here oxidation state of this sulfur is +5, 0, 0, +5. Now, in this reaction, first you balance this reaction. In this reaction, total 4 sulfur atoms are participating. The oxidation state of the first sulfur is 0. Next sulfur is +4. Similarly, in another molecule, 0 and +4. Total oxidation state +8. This side 4 sulfur atoms are present. First sulfur +5, second sulfur 0, third sulfur 0, fourth sulfur +5. Here total +10. The difference is 2 units. This difference is 2. That means 2 thiosulfate molecules upon participation have released 2 electrons. Therefore, valency factor of the thiosulfate. Valence factor of Na2S2O3. Number of electrons lost by number of molecules. Number of electrons by number of molecules. Number of electrons 2, number of molecules 2, therefore 1. Valence factor of the hypo. Therefore, whenever if iodine and hypo react with each other, you remember the valence factor of the iodine and hypo, then simplification becomes very easy. Next, another well-known redox reaction is reaction between the I- and CuSO4. In this reaction, Cu2I2 will be formed. Next Cu2I2, next I2, next sulfate. In this reaction, this is also well known redox reaction. and very important for numerical calculations. Therefore, first let us discuss the calculation of valence factor of the copper and iodide. Here, see, for iodide, we will take the iodide in the form of potassium iodide or so. Therefore, in this case, first if you balance, we can balance it. Otherwise, without the need of balancing, directly we can proceed. So, valence factor of iodide. Valence general formula is number of electrons by number of molecules. Number of electrons lost by number of molecules. Number of molecules. Here, number of electrons lost. One iodide is losing one electron. Number of molecules, so on. So for potassium iodide or iodide, valence factor is 1. Next for copper. For copper, we have to balance these copper atoms first. Here on the reactant side, we have 2 copper atoms. Each copper is in +2 oxidation state. This side, the 2 copper atoms, they came here. The oxidation state of each copper is +1. Therefore, total oxidation state here is +4. Here total oxidation state is +2. So difference is 2 units. That means this copper sulfate is gaining 2 electrons. So how many molecules are gaining 2 electrons? 2 molecules. Therefore, valency factor. Valency factor of copper sulfate. Number of electrons lost. Therefore, here gaining. Therefore, number of electrons gain. Number of molecules. Number of electrons gained. How many electrons? 2. Number of molecules 2. So, therefore, 1. Therefore, 1. So, for copper sulfate, valence factor is 1. Next, another well-known example in the redox reactions is reaction between the hydrogen peroxide and permanganate. So, if the reaction takes place in acidic medium, this permanganate will be reduced to Mn2+. H2O2 will be oxidized to the water and oxygen. So, in all redox reactions, the valence factor of hydrogen peroxide, valence factor of H2O2 is always 2. Since the reaction is taking place in acidic medium, valence factor of MnO4 minus is 5. Therefore, equivalence of H2O2 is equal to equivalence of MnO4 minus. In place of equivalence, we can use any formula for H2O2 as well as any formula for MnO4 minus. Next, another well-known example is bleaching powder. When bleaching powder participates in any reaction, it will be converted into calcium chloride and it will supply the nascent oxygen. So here one molecule of the bleaching powder will always supply one nascent oxygen. In this change, what is the valence factor of the bleaching powder? See here, before participation in the reaction, this is a bleaching powder, OCl minus, this one. Here the oxidation state of the chlorine is -1. Here oxidation state of this OCl minus is minus, but therefore oxidation state of the chlorine is +1 here. Oxidation state of the oxygen is -2. Therefore, when bleaching powder participates in the reaction, this oxygen is coming out. It is coming out of the molecule by keeping its extra 2 electrons within the molecule. That means here totally 2 electrons are being exchanged. Therefore, valence factor of bleaching powder is again 2. So, when the bleaching powder is used in any reaction, use the valence factor 2 for simplifications.